You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Continuous integration, often shortened to CI, and API automation have become cornerstones of modern development and security operations. The primary goals of these practices are to deliver changes safely, verify security checks early, and speed up deployment cycles without sacrificing trust. In a traditional development model, teams would integrate code changes only after long intervals, leading to integration failures, security surprises, and unstable releases. CI changes this by requiring developers to merge their changes frequently into a shared repository, where automated builds and tests run continuously. API automation complements this by providing programmable, repeatable ways to configure infrastructure, enforce policies, and manage deployments. The combined result is faster feedback loops, fewer manual errors, and a higher degree of confidence in every release. For security, these practices provide an opportunity to shift left, embedding checks early in the pipeline rather than relying on late-stage reviews. This creates a culture where every change is tested for functionality and compliance before it ever reaches production. One of the most powerful aspects of CI is the integration of security checks directly into the pipeline. Instead of waiting for security teams to review code after development, automated tools run continuously with each commit. Static Application Security Testing, or SAST, scans code for vulnerabilities like injection flaws or unsafe functions. Secret scanning checks for hard-coded credentials such as API keys or passwords, which are frequent and dangerous mistakes. Dependency checks analyze open-source libraries to flag known vulnerabilities before they make it into production. Infrastructure as code linting reviews templates for insecure configurations, like open security groups or unencrypted storage. By embedding these checks into the CI pipeline, teams catch issues when they are cheapest to fix before they are deployed. This transforms security from a bottleneck into an integrated quality gate. For learners, it helps to think of CI like an assembly line, with inspectors at every station, rather than only at the very end. CI pipelines are typically organized into stages, each building confidence that code is ready for the next step. The first stage is the build, where code is compiled and packaged into artifacts such as executables, containers, or infrastructure templates. Next comes testing, where unit and integration tests confirm functionality. Security gates follow, running scans such as SAST, dependency analysis, and policy checks. Only if all these succeed does the artifact proceed to promotion, where it is stored in a registry for deployment. This staged approach ensures that code is not only functional, but also secure and compliant before advancing. Importantly, failures at any stage stop the pipeline, preventing risky changes from slipping forward unnoticed. For learners, imagine building a car where each station engine assembly, brake testing, safety inspection must pass before the car rolls to the next stage. CI pipelines work the same way, promoting only code that meets every quality and security requirement. Artifact provenance and signing are critical for ensuring that the code deployed in production is exactly what was built and approved earlier. Provenance refers to the traceable history of an artifact, showing when it was built, what code and dependencies it included, and which tests it passed. Signing provides cryptographic assurance that the artifact has not been tampered with between build and deployment. For example, a container image signed at build time can be verified before deployment, ensuring it is genuine and unchanged. Without provenance and signing, attackers could inject malicious code into deployment pipelines, and teams would have no reliable way to detect it. Provenance also aids audits, providing a chain of custody for every artifact. For learners, think of it like a sealed envelope stamped by the sender. When you receive it intact, you know it has not been altered. Artifact signing provides that same assurance for digital builds. Credential management is one of the most sensitive areas of CI. Build agents and pipelines often need temporary access to repositories, registries, or cloud platforms. The best practice is to use ephemeral credentials, short-lived tokens, issued for the duration of a build, and revoked immediately afterward. This prevents the risks of long-lived credentials, which can be leaked or stolen and remain valid indefinitely. For example, a build pipeline might request a token from a vault at runtime, use it to pull dependencies, and discard it when finished. If an attacker compromises the pipeline logs or environment, the token is already expired. By contrast, hard-coded or static credentials turn pipelines into persistent attack surfaces. For learners, ephemeral credentials can be compared to visitor badges in secure buildings. They grant access only for a limited time, and once the visit is over, the badge is useless. This ensures access is controlled, temporary, and auditable. Application Programming Interfaces, or APIs, make automation of configurations and security enforcement possible. Infrastructure as Code, or IAC, defines systems and declarative templates that can be version controlled and tested. Policy as Code takes the same approach for security rules, encoding them into files that pipelines can enforce automatically. API automation ensures these policies are consistently applied without human intervention. For example, an API call could ensure every cloud storage bucket has encryption enabled, or that every new server is tagged with compliance labels. This eliminates the variability of manual configuration and ensures governance at scale. The advantage is consistency. No matter who deploys the system, the API ensures it meets the same standards. For learners, this is like using a recipe rather than relying on memory. API automation turns configuration into repeatable, testable code, reducing human error while enforcing security across environments. Testing APIs requires more than checking whether they return the right responses for expected inputs. Integration testing validates that APIs conform to contracts agreed upon between systems, ensuring that the fields, formats, and behaviors align correctly. Schema validation goes deeper, confirming that data structures remain consistent across updates. Negative testing explores how APIs handle invalid, unexpected, or malicious inputs, which is critical for security. For example, a negative test might send malformed JSON or excessively long input strings to see if the API fails safely rather than crashing. These tests prevent fragile integrations that might break or create vulnerabilities when conditions deviate from the norm. For learners, think of API testing like rehearsing for both good and bad weather before a long road trip. You do not just test the car on a sunny day, you also make sure it can handle rain, snow, and potholes. Robust API testing ensures resilience under real-world conditions. Rollback patterns are safeguards for when deployments go wrong. Immutable artifacts ensure that what is deployed cannot be modified in place, reducing the risk of configuration drift. Tagged releases allow teams to roll back to the last known good version quickly without rebuilding from scratch. Fast rollback procedures provide confidence to deploy more frequently because mistakes can be reversed easily. For example, if a new release introduces a bug, the pipeline can automatically redeploy the last stable artifact. Without rollback patterns, teams may hesitate to deploy often, fearing that failures will require manual, time-consuming fixes. With rollback patterns, deployment becomes safer, faster, and more resilient. For learners, rollback can be compared to a safety net in a circus act. Performers can attempt daring moves because they know if something goes wrong, the net is there to catch them. Rollback patterns give development teams that same safety and confidence. Observability in pipelines ensures that automation is not only functioning but also measurable. Build metrics track how often builds succeed or fail, providing insight into pipeline health. Signals of test flakiness tests that sometimes pass and sometimes fail highlight instability that undermines trust. Security gate pass rates measure how often builds meet compliance checks versus being blocked. Together, these metrics provide transparency into how reliable and secure the pipeline truly is. Dashboards displaying this information allow both developers and security teams to see trends, troubleshoot problems, and identify weak spots. For learners, observability can be compared to the gauges on a car's dashboard. They show whether the engine is healthy, how much fuel is left, and when maintenance is needed. Without them, you would be driving blind. Observability ensures CI pipelines are not black boxes, but transparent systems that can be monitored and improved continuously. Environment parity is another best practice for reducing production surprises. The idea is to keep development, staging, and production environments as similar as possible. Staging mirrors should replicate production closely, using the same configurations, libraries, and versions. Sandboxed runs allow pipelines to simulate deployments safely, catching errors before they affect live users. Without parity, changes that worked fine in development may fail in production due to subtle differences. Maintaining parity reduces this risk and increases confidence in every release. For learners, environment parity is like practicing on a flight simulator before piloting a real plane. The closer the simulator is to reality, the more reliable the practice. Staging and sandboxed environments provide that safe rehearsal space, ensuring deployments are stable when promoted to production. Governance in pipelines ensures changes are controlled, reviewed, and auditable. Just as production changes require approvals, pipeline changes, such as new scripts, updated security gates, or altered workflows, must also be governed. Reviews and approvals confirm that changes are safe, consistent, and aligned with policy. Emergency bypass controls may exist for urgent fixes, but must always be followed by post-facto audits to ensure accountability. Without governance, pipelines can drift into chaos, with ad hoc modifications that bypass controls and introduce risk. With governance, pipelines remain stable, reliable, and compliant. For learners, governance is like traffic signals at busy intersections. Without them, cars might collide, even if most drivers act carefully. Governance keeps automation moving safely, ensuring pipelines empower rather than undermine security. A practical starter exercise demonstrates how to embed these ideas. Take one existing CI pipeline and add a secret scanning stage, plus a software composition analysis, or SCA, check for vulnerable dependencies. Configure the pipeline to fail builds automatically when high-risk secrets or known vulnerable libraries are detected. Then document the remediation workflow, who investigates, how fixes are prioritized, and how corrected builds are validated. This simple step immediately reduces risk by catching two of the most common and dangerous issues in development: leaked secrets and insecure libraries. It also provides a model for extending security checks across other pipelines. For learners, the lesson is that CI security does not need to start with massive overhauls. Small, incremental steps like secret scanning produce outsized security benefits while building momentum toward fully mature automated security pipelines. Checkmark. That's episode 160, part 1 complete. 15 paragraphs, 175 plus words each, narration ready, deeply explanatory. Policies code is one of the most transformative practices in secure CI pipelines. Instead of relying on human reviewers to manually check whether infrastructure or applications meet standards, rules are written as code and executed automatically. For example, if a cloud security policy requires encryption on all storage buckets, a policy as code engine evaluates every configuration file during the CI process and fails the build if the rule is violated. This approach makes compliance consistent, repeatable, and free of human subjectivity. Policies can reflect industry standards like CIS benchmarks or custom organizational rules, and because they live in code, they can be versioned, tested, and audited just like any other software artifact. For learners, think of policy as code as a guardrail built directly into the road. Instead of relying on every driver to stay perfectly centered, the guardrail prevents veering into dangerous territory. It ensures pipelines enforce rules automatically before unsafe changes can ever be deployed. API resilience is another area where CI adds value, particularly through testing rate limits and throttling. Modern applications rely heavily on APIs, And under load, those APIs can become bottlenecks or even fail entirely. CI pipelines can simulate high traffic against APIs, testing whether they enforce rate limits gracefully, throttle responses instead of failing outright, and maintain service availability under pressure. This testing ensures resilience, preventing denial of service conditions caused not by attackers, but by normal usage spikes or poorly coded integrations. For example, an API that handles 100 requests per second in testing, but collapses at 1,000, will be flagged long before it reaches production. For learners, it is useful to imagine practicing crowd control at a stadium before the big game. If gates jam during the drill, you fix the problem in rehearsal instead of during the actual event. Rate limit testing in CI provides that rehearsal, validating APIs can withstand stress. A common question in automation is the difference between continuous delivery and continuous deployment. Continuous delivery means every build that passes tests and security gates is automatically prepared for deployment, but a human makes the final decision to push it live. Continuous deployment removes that human checkpoint. Every approved build goes straight into production. Delivery balances speed with control, while deployment maximizes automation and velocity. For security, the trade-off lies in risk tolerance. Continuous deployment requires extreme confidence in automated tests, gates, and rollbacks because human review is absent. Continuous delivery still allows security teams to inject judgment for sensitive systems, such as financial services or healthcare platforms. For learners, this is like choosing between autopilot that requires a pilot to confirm landing versus autopilot that lands the plane itself. Both approaches work, but they demand different levels of trust in the underlying automation. The choice depends on business risk appetite and regulatory context. Canary and staged rollouts are another safety net provided by CI pipelines. Instead of deploying a new build to all users at once, a canary rollout deploys it to a small subset first. Automated health checks then monitor error rates, latency, and user experience for that group. If results are positive, the deployment expands to larger groups until it reaches everyone. Staged rollouts work similarly, breaking deployment into phases that provide checkpoints for validation. This reduces blast radius, ensuring that bugs or vulnerabilities affect only a fraction of users before being detected. Automated health checks tied to these rollouts make the process proactive. Issues are caught early without waiting for user complaints. For learners, think of this as test marketing a product in one city before launching nationwide. If something goes wrong, adjustments can be made locally before scaling up. Canary and staged rollouts make CI pipelines safer and more reliable. Artifact registries serve as the central warehouses for build outputs, and their security is paramount. Registries hold container images, executables, and configuration artifacts that pipelines produce. If compromised, they become perfect delivery mechanisms for malware, since poisoned artifacts are automatically deployed. Securing registries involves strong access controls, ensuring only authorized pipelines and users can push or pull artifacts. Immutability should also be enforced, meaning once an artifact is published, it cannot be altered, only replaced with a new version. Signing artifacts adds cryptographic assurance, ensuring that only verified builds are deployed. For learners, it helps to think of a registry like a pharmacy. The bottles must be sealed, prescriptions controlled, and every product traceable to its source. Without these safeguards, attackers could substitute malicious medications into trusted supply chains. Registry security transforms artifact storage from a passive repository into an actively defended checkpoint in the pipeline. Automation does not end at deployment. Post-deploy scans and runtime validation close the loop. Even if code passes all pre-deployment checks, runtime environments may drift. Drift occurs when configurations change unexpectedly, vulnerabilities emerge in dependencies, or unauthorized modifications slip in. Automated post-deploy scans catch these deviations. For example, a runtime validation tool might detect that a container no longer matches its signed baseline, indicating tampering or misconfiguration. Automated scans also check for vulnerabilities that became public after the build, ensuring systems remain protected over time. For learners, runtime validation can be compared to airport security, not just screening passengers before boarding, but also conducting in-flight checks. Security does not stop once the plane is in the air. It must be maintained continuously. Post-deploy scans ensure that deployed systems remain as secure as when they first passed through CI gates. Secrets injection patterns are critical during deployment. Applications need credentials to talk to databases, APIs, and other services, but embedding these secrets in code or artifacts is insecure. Instead, pipelines should inject ephemeral tokens or use workload identities provided by cloud platforms. Vault integration provides another option, retrieving secrets securely at runtime without exposing them in logs or files. This ensures that even if an artifact is compromised, no static credentials are included. Ephemeral tokens and workload identities also support automatic rotation, reducing long-lived secrets that attackers can target. For learners, secrets injection can be compared to giving a delivery driver a temporary key card that only works during their shift. Once the work is complete, the card expires, and no permanent key is ever left behind. This keeps deployments functional but safe, with credentials managed dynamically instead of statically. Automated remediation hooks extend CI pipelines into operational safety. If a deployment fails a health check, the pipeline should automatically roll back to the last good version rather than waiting for human intervention. Notifications should also be routed to safe channels, such as operations chat groups, ensuring visibility. This combination of auto rollback and safe notified channels ensures incidents are contained quickly and transparently. Without these hooks, a failed deployment may linger unnoticed, compounding impact. With them, issues are self-healing, allowing teams to focus on investigation rather than urgent triage. For learners, this can be compared to a car with automatic emergency braking. If a collision is imminent, the car intervenes instantly, rather than waiting for the driver to react. Automated remediation hooks bring that same proactive safety to CI pipelines, ensuring resilience under failure conditions. Measurement is essential to track the effectiveness of CI and API automation. Useful metrics include build-to-deploy lead time, which measures how quickly code moves from commit to production, failure rates, which show how often builds or deployments break, and the percentage of builds blocked by security gates, which indicates how effectively vulnerabilities are caught. These metrics provide transparency into pipeline efficiency and security. For example, if failure rates spike, it may mean tests are too brittle or code quality is slipping. If security gate blocks rise, it signals improved detection, but may also highlight the need for developer training. For learners, metrics function like fitness trackers. They do not guarantee performance, but provide data that guides improvements. By tracking CI pipeline metrics, organizations gain visibility, identify weak points, and demonstrate progress over time to both technical and executive stakeholders. Blue/green deployments and A/B testing are advanced strategies enabled by CI orchestration. Blue/green deployments maintain two environments: one live blue and one idle green. New versions are deployed to the idle environment, and traffic is switched only when validated. This provides near-instant rollbacks if issues appear. A/B testing takes a different angle, splitting traffic between two versions and comparing results. This allows teams to evaluate performance, user experience, or security impact in real time. CI pipelines orchestrate these strategies by managing environments, switching traffic, and collecting metrics automatically. For learners, imagine running two restaurants side by side. One serves the current menu, while the other tests a new recipe. Customers vote with their choices, and management decides when to roll out changes broadly. These patterns provide safer experimentation and deployment, reducing risk while enabling continuous innovation. Developer training is a crucial yet often underestimated part of CI security. Pipelines can only enforce what is coded, and if developers consistently push insecure code, automation becomes clogged with failures. Training ensures developers understand secure coding practices, proper secret handling, and how to interpret pipeline feedback. CI linting tools reinforce this by scanning code for style, quality, and security issues before it even reaches the pipeline. Together, training and linting reduce the number of issues that reach later stages, increasing pipeline efficiency. For learners, this is like teaching chefs to prepare ingredients properly before cooking. If preparation is sloppy, the dish fails no matter how good the oven is. By investing in developer training and pipeline linting, organizations ensure their CI systems are not overloaded with preventable issues. Security becomes a shared responsibility across the lifecycle, starting with the developers themselves. In the end, continuous integration and API automation succeed when security is baked into every stage. Pipelines must automate checks for vulnerabilities, enforce policies as code, and rely on ephemeral credentials to protect secrets. Artifacts must be signed to guarantee provenance, and rollback mechanisms must provide safety nets when deployments fail. Observability ensures transparency, while canarying, blue/green testing, and post-deploy scans keep systems stable in production. Governance, developer training, and careful measurement tie the program together, ensuring continuous improvement. The lesson for learners is clear. Automation is not just about speed. It is about safety, resilience, and trust at scale. Organizations that master CI and API automation build systems where every change is tested, secured, and monitored before it reaches users. This transforms pipelines from fragile conduits into strong, reliable engines of secure digital delivery. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.